So, we begin the first chapter. I will be talking about ordinary differential equations. Let us discuss the genesis of ordinary differential equations. Where do they come from? And then we will move on to first order ordinary differential equations. So, ordinary differential equations appear everywhere. They come to you uninvited. They come to your doorstep uninvited. How? When you take up balance laws in science, when you formulate them mathematically, what comes out is an ordinary differential equation. For instance, if you take in physics, the balance laws are given by Newton's laws of motion, mechanisms operating in ecological systems, population dynamics. For example, you will see systems of differential equations arising when you model heartbeat. Hodgkin and Huxley were awarded the Nobel Prize for modeling the heartbeat. They appear in geometrical optics. They appear in the form of partial differential equations, ordinary differential equations, and so on. It appears. I can give you a long list, and this list can continue forever. So, so let's look at some examples. So, let us take a simple example from geometry. Let us take a family of circles, what I should think of this as a toy example. Let us look at a family of circles touching the x and y axis, right? You have the x and y axis, and a circle touches the x axis and y axis. So, the center should be what? R comma r, and the radius is also r. So, the equation is simply x minus r squared plus y minus r squared. So, now that can be simplified, and now, so that is the differential, that is the equation for such a circle. It is a one parameter family of circles parameterized by r. You differentiate with respect to x. What do you get? You get x plus y dy by dx minus r dy, which can be written as, I have just written it in simpler form and called it equation number 3. So, now you eliminate the parameter between 1 and 3, and what you get? You eliminated the parameter. What will be what will remain is a relationship between x, y, and y prime, and it's quite a monstrous looking thing, but starting from a one parameter family of curves in the plane, you have gotten a differential equation. I leave it as an exercise for you to simplify equation 4. Many terms will cancel out, as you can see. The x squared term from the first group of things will cancel out completely. There is an x squared coming from the first term, there is a minus 2x squared coming from the second term, and there is an x squared coming from the third term. That will cancel out. There will be lots of cancellations. You can please try this as the first exercise for the course is on up there. Simplify this expression. Next. Now, let us take the next example. This time the example comes from physics. So, let us consider a pendulum, a simple pendulum. What is a simple pendulum? It's simply a spherical mass that is hanging from a vertical string of length L. L is the length of the pendulum, and when it is hanging vertically, you just displace it slightly and let it oscillate. So, what is the variable that you are trying to understand? The displacement, the angular displacement theta is what you are looking at, right. So, let us consider a pendulum of length L. Theta denotes the angular displacement from the mean position, right. So, what is the balance law that is operating here? Well, so the mass of the pendulum, the pendulum has length L, m is the mass, and so its moment of inertia is going to be ml squared. And so, if moment of inertia multiplied by, what is d2 theta by dt squared? It is the angular acceleration, right. The angular acceleration multiplied by moment of inertia gives you the torque, and this torque is getting balanced by the torque due to the gravity. Gravity is pulling it vertically downwards, the force is mg acting vertically downwards, and so mg L sin theta will be the torque caused by the force of gravity. So, these two forces must balance. You see, the Newton's second law of motions, what does it say? It says that mass times acceleration is the impressed force, right. Now, here it is not a, here what is happening, it is a rotational motion, right. The pendulum is performing some kind of a rotational motion. So, instead of mass, the correct object will be moment of inertia. Always when you go from a linear, from rectilinear motion to rotational dynamics, the role played by mass will be played by moment of inertia. Instead of the acceleration, you have the angular acceleration, right. So, instead of ma, you have moment of inertia times the angular acceleration, and instead of the force, you have the torque. If you take the Newton's, it follows on the Newton's laws only, it is a slightly adapted version of Newton's law, correct. So, the balance law is written down now, ml squared d2 theta by dt squared, which is the angular acceleration multiplied by moment of inertia. This must be balanced by the torque. What is the torque? Minus mgl sin theta. Why the minus sign? Because of the as theta increases, it is acting in the downward, in the opposite direction. They act in opposite directions. So, you equate them, and what do you get? You get the equation star, which is d2 theta by dt squared plus g over L sin theta equal to 0. So, you see that this is the equation of the simple pendulum. Of course, I understand that many of you may have forgotten your physics or may not have studied physics at all. Do not worry, just remember what is the basic thing. The basic thing is that it is a balance law of some sort. Some balance law in physics gives rise to this equation. That is the philosophy that we have to capture. That is all that is important in this whole thing. The details are not important. What is angular acceleration? What is moment of inertia? If you have forgotten, just don't pay it. Just don't worry about it. Just remember that this gives you a gist of how a balance law from physics gives rise to a differential equation. So, this is the differential equation for the simple pendulum. Is it clear? Shall we proceed? Anybody is writing down anything? Okay. Now, it is very customary to look at small oscillations of the pendulum, right. You just only look at when the pendulum has only performing small oscillations. Then what do? You replace sin theta by theta. This is a standard thing that physics books are doing all the time. So, see, why are we doing this? One may ask, why not just, what is the purpose of doing this sin theta, replacing sin theta by theta? Simply because sin theta is a complicated function and theta is a simpler function. More than that, sin theta is a non-linear function. Sin of theta 1 plus theta 2 is not the same as sin theta 1 plus sin theta 2, right. It is not a linear function, whereas theta is a linear function. So, replacing sin theta by theta, what you have done is you have replaced the non-linear differential equation star. Why is it a non-linear differential equation? The second term, if you look at, there is a expression in theta which is non-linear. The first term d2 theta by dt squared is a linear expression, right. If you replace theta by theta 1 plus theta 2, you get a sum, right. Come in please. d2, the second derivative of theta 1 plus theta 2 is the sum of the second derivatives. Differentiation is a linear operator, correct. So, first term is linear. The second term g over L sin theta is a non-linear expression. The non-linear expression has now been replaced by a linear expression. What is that linear expression? Theta double dot, the dot refers to differentiation, the second derivative of theta plus g over L theta equal to 0. This is a linear differential equation. So, linear differential equations are, one understands it, are easier to handle than non-linear differential equation. So, what this is the equation of a harmonic oscillator. Right. So, yeah, the comment that I made is now appears explicitly. The equation theta double dot plus g over L sin theta is non-linear. The non-linear term has been underlined in red, but its approximation is a linear ODE. Now, I am not giving you a very precise definition of what is a linear ODE. I can tell you what it is. A differential equation is said to be linear if it obeys the superposition principle. If y1 and y2 are two solutions, then c1 y1 plus c2 y2 is also a solution. So, if you look at the harmonic oscillator, theta double prime plus g over L theta equal to 0, you can check that if theta 1 and that if you have two solutions y1 and y2, then c1 y1 plus c2 y2 is also a solution. This result fails for the nonlinear equation for a pendulum. If instead of theta, if you have sin theta over there, this result is no longer true. So, you understand what is a linear differential equation, right? Linear differential equations are those which obey the superposition principles, like the waves, right? Waves obey, you superimpose two waves, you take linear, just linear combinations. I mean, mathematicians would use the word linear combinations, whereas engineers and physicists would use the phrase superposition principle. Okay, is it clear? So, now let us take the third example. This time we are taking an example from biology or ecology. Let us look at an ecology, a two species ecology. Right now, let us consider there are various two species ecologies we can think of, but let us look at a very special case. After all, we are only looking at examples just to illustrate why differential equations are important, where do they come from. We are still at that subject. So, let us assume that the two species of the two species, one of them is a predator and one of them is a prey. So, for example, the predator, let us think of them as sharks, and let us think of the prey as sardines. Sardines, the prey, will live on algae. They are vegetarians, whereas the sharks are non-vegetarians, right? So, now we have to understand what is the population dynamics. So, let us say that X is the population of sharks and Y is the population of sardines. Now, it turned out, let me give a little bit of history. It is well known, this history is very well known, it is there in most of the books. Between the two world wars, D'Ancona was the head of the fisheries department in Trieste. Trieste is in Italy, and there was hostilities between Austria and Sicily, and so the fishing activities had declined in the upper Adriatic. What D'Ancona observed is that he made a statistical study of the fish population, and this was the fish population was basically there were predominantly two species, one of them was a predator and one of them was a prey. He observed that in a period of 20 years, the population of the two species underwent cyclic changes, and these cycles were out of phase. Secondly, the decline in fishing activity was favorable to the predators. So, he wanted to understand why is this the case. So, he goes to his mathematical friend Lotka-Volterra, and Lotka-Volterra constructed a model, a mathematical model for this, and he was able to explain D'Ancona's observations quantitatively. He also went ahead and continued his studies of population dynamics, and he wrote a monograph on that. That is a very long subject. Ecological models is a very long topic, but we shall just look at the differential equation that arises. Now, suppose, now remember, X is a population of sharks. Suppose that there were no sardines at all. There is only sharks are there in the lake. Then what will happen? Their population will rapidly decline. Correct? There won't be any food for them, and there will be an exponential decline in the population. And so the differential equation would look like dx by dt equal to minus ax, exponentially dying down. On the other hand, if you look at if you were to look at only sardines are there, then there are no predators, there are no sharks, so they thrive, and their population will increase exponentially. That would be the, so now what we do is that we put the two together to get a two species ecology, right. Now what do you get? X dot equal to minus ax, the exponential decline due of the population of sharks is going to be balanced by some term, correct. It is going to be checked by a positive term plus bxy. On the other hand, the exponential increase cy, remember that in the second differential equation y dot equal to cy, if just the cy is present, it will exponentially increase, but that is going to be checked by minus dxy by a term. Now you might ask, why bxy, why not bx squared y squared or dx cube y to the power 7? That would be a natural question that would come to you. Just imagine, suppose you have in the neighborhoods, you have mice and you have cats, correct. Now suppose you double the population of cats and double the population of mice, then a cat is going to likely to encounter a mice 4 times as frequently, correct. It is going to multiply, and this interaction is going to be unfavorable to the mice and is going to be favorable to the cats, and so there will be a plus sign when you look at the predator, and there will be a minus sign when you look at the prey. You can also consider other possibilities. One can consider cubic terms, but they will be further approximations, there will be finer, better approximations, etc. But to a first approximation, this is the system of differential equations. X dot equal to minus ax plus bxy, y dot equal to cy minus dxy. You have a pair of differential equations. It is a pair of non-linear differential equations. Where does the non-linear term come from? It is the xy terms that is responsible for the non-linearity. So this is a system of differential equations. So this time we have a system of first order ODE. For the case of a pendulum, we got a one single differential equation, a scalar ODE, second order ODE, whereas here we have a system of first order ODEs. Later on we will undertake a careful study of this system of differential equations. This is called the Lotka-Volterra system. It is a very famous system of differential equations. Volterra I already explained to you. Lotka was studying chemical reactions, and when you study chemical reactions where there are a number of constituents, reactants and products, and then the system of differential equations look very similar. You have a polynomial systems. They are system of polynomial differential equations. If you have a chemical reaction where there are 5 different chemicals are interacting and producing others, then you will have a large system of differential equations, and they are typically of a polynomial type. On the right hand side will be polynomials in several variables. So those are those kinds of systems have been studied by chemists. There are some number of famous ones are available, but we shall return to this later in greater detail. So we have talked about genesis of differential equations, how they arise, why are they important, why should we study them. Now let us look at, of course all this must be familiar. I mean perhaps some of the things were not familiar to you. Maybe the Volterra-Lotka was not familiar to somebody. Maybe pendulum equation is probably more familiar, and there are other examples you may have encountered: electrical circuits, mechanical circuits, springs, hard springs, soft springs, LCR circuits where there is an inductance, capacitance and resistance. Various systems I am sure you have encountered. And what I am going to tell you now, methods for handling first order ODEs. Some of these things are probably very familiar to you, but let us just for completeness, let us go through, let us have a quick roundup. Let's not just leave it. Later on, we'll realize, oh, this we don't remember. We have studied this, we have taught this, but we don't remember. But let's have a quick roundup for completeness. So let us take the Lotka-Volterra system. What was the Lotka-Volterra system? X dot equal to minus ax plus bxy. Y dot equal to cy minus dxy. I had taken the same pair of functions and I divided one by the other. So dx by dt divided by dy by dt. What will that be? By chain rule, it will be dx by dy. Correct. And what do I get? Dx by dy equal to minus ax plus bxy divided by cy minus dxy. This is very conveniently written. This is of course in calculus courses you keep telling your students that dx by dy comes as a piece. You can't separate the dx and dy. But then the chain rule, how does the chain rule looks? Dy by dx equal to dy by du into du by dx. It's as if you can cancel the du and the du, right? It just formally looks. I mean, so with the same kind of analogy, we will just for convenience write this differential equation as cy multiply by cy minus dxy and multiply by y. It's not multiply by dy. And so what you write down is cy minus dxy dx plus ax minus bxy dy equal to 0. This is a way of writing the differential equation. Okay. Now don't ask what is dx and what is dy. What is it? You have to interpret it as the previous equation. This is the conventional form in which a first order ODE is written down, right. Now why I have put a dot under the d, and there is a reason is that it's a very unfortunate circumstance that the dx appears, the d appears in the dx, and here the d with a dot underneath is a constant, just to distinguish the dx and the d times x, I put a dot under the d, okay. So I have written that comment also, d in the expression c minus dx denotes a constant, an unfortunate choice, but let it be. I mean, let us now take this equation and let us divide it by xy, and a nice thing and a very pretty thing happens. What is happening? You have c by x minus d into dx plus a by y minus b into dy equal to 0. This is an example of what is called as a variable separable equations. It's a variable separable equations because the variables have been separated. One of them, there are two pieces. One piece involves only x and the other piece involves only y. And what is the next thing to do? To integrate. Okay. Shall we do that? A single integration gives you c log x minus d plus a log y minus b equal to e. What is that e out there? It is the constant of integration. It is a constant that arises out of integration. Whereas the a, b, c, d are also constants, but they are the given constants that appear in the differential equations. They are the various population parameters and whatnot. Right? The e is the constant of integration. So we have thus obtained a general solution of the ODE. The ODE has been rewritten for your convenience. So the ODE has a general solution. That is when the general solution will involve a arbitrary constant that arises out of integration. So this is something that this is sort of a business that you are quite familiar with, and I am sure you must have solved numerous exercises. You must have given numerous exercises of this kind to your students to solve. But anyway, we just for completeness, we have just looked at one single example. And the example that we looked at came from the Volterra-Lotka system, and there is a reason why I did this completely, because we are going to use this expression c log x minus d plus a log y minus b equal to e for analyzing the Volterra-Lotka system later in the course. Okay. Another type of differential equation of first order is a homogeneous equation. This is also something that you are probably familiar with, but let us but this is more interesting and less trivial. So, consider the first order scalar ODE m dx plus n dy equal to 0, where m and n are functions of x and y. When is a function of two variables said to be homogeneous? What does homogeneity really mean? It means that the function, that is when you replace x and y by tx and ty, some power of t can be pulled out, right. That is what the definition. Recall that a function f of x y is said to be homogeneous of degree c if f of tx comma ty equal to t to the power c times f of x y, and c is called the degree of homogeneity. So, many expressions like say x squared plus y squared plus z squared is homogeneous of degree 2, whereas x cube minus 3x squared y and 3x y squared minus y cube are homogeneous of degree 3. ln x minus ln y is homogeneous of degree 0, because when you replace x and y by tx and ty, the log t will cancel out, right. Okay. In the right, there is a dx and there is a by. Thank you. And that is exceedingly important, that x and the y there are very, very important. So, homogeneous equations. So, you understand what a homogeneous function is. So, now what are we requiring? We are requiring that m of xy and n of xy are both homogeneous of the same degree. What exactly does it say? It means the differential equation exhibits a symmetry of a certain type. A variable separable equation is also exhibits a symmetry of a certain type. You have a sum of two terms, one term involves only x and another term involves only y. That is a kind of a symmetry, if you like. Here it is a symmetry of a different type. There is a, I would call it a scaling symmetry. The ODE exhibits scaling symmetry. Whenever differential equations have symmetries, then there are certain ways of solving them, special ways of solving. Now, you might ask the following question. There could be presumably other types of symmetry. Why should you scale x also by t and y also by t? Why should you replace x by tx and y by ty? You could replace x by tx and y by t squared y, and something may happen. That is also a symmetry. It is called a weighted homogeneous function. A function f of x y, I would call it a weighted homogeneous if when you replace x by t to the power alpha x, y by t to the power beta y, it's the t to the power gamma comes out, and if f of x y. You can think of more exotic examples of this kind, and there will be corresponding solution techniques for that. The thumb rule, the philosophy is that whenever there is a symmetry, there will be a special way of there will be special techniques for solving it. That's a guiding philosophy in the theory of differential equations. Okay, so then let us now stick to the simplest type of symmetry, the scaling symmetry, namely x is replaced by tx and y is replaced by ty, and a t to the power c comes out, and m and n are homogeneous of the same degree. Let us just stick to this simple example. And then what do we see? Suppose m and n are homogeneous of the same degree, then the differential equation m dx plus n dy equal to 0 can be transformed into a variable separable equation. There will be corresponding theorems for weighted symmetries also. And then of course, the transformation, how do you do the transforming? That will change, of course, it will depend upon the symmetry. Okay, so let us now study this simple example. So, what is the substitution that you are going to make? Y equal to zx. This is an obvious substitution because y by x is your t. When you are replacing x by tx and y by ty. So, y by x does not change under the transformation. So, the new variable z will be y by x. Okay. So, now let us take this y equal to zx and see what happens. dy by dx is z plus x dz by dx, and which is more conveniently written as dy equal to z dx plus x dz. Put it in the differential equation and see. M of x y, but y is zx. So, m of x comma zx dx plus n of x comma zx dy is what? Z dx plus x dz equal to 0. X to the power, now because of the because m and n are homogeneous of the same degree c, x to the power c comes out from both the expressions m and n and cancels out, and you are left with m of 1 comma z dx plus n of 1 comma z z dx plus x dz equal to 0. And that will simplify as m of all the z terms together been grouped, and that is plus dx plus x n 1 comma z dz. Is it correct? The second last line in the slide, which is a variable separable equation. Correct. So, a homogeneous differential equation can be transformed into a variable separable equation by a simple transformation. What is the transformation? Y equal to zx. Let us now apply all this to a very simple example rather than rather than focus on the theorem. Why not just look at a simple example? I have taken a quadratic differential equation, x squared minus y squared dx minus 2xy dy equal to 0. It is obviously a homogeneous differential equation. Let us put y equal to zx, and then we will get the obvious simplifications, x squared into 1 minus z squared from the first term and 2x squared z from the second term, and the dy will get replaced by z dx plus x dz, and the x squared will cancel out, and then you have the other terms 1 minus z squared minus 2 dx minus 2z squared dx minus 2xz dz equal to 0. I hope I have not made a mistake in the algebra, but if the algebra is correct, then you see that you have to first divide by x to get the dx by x, and then you have to divide by the coefficient of dx, which is 1 minus 3z squared, right. So, you get, so is it correct? Dx by x minus 2z dz upon 1 minus 3z squared equal to 0, variable separable. And this is the way you would do it. I mean, you would not remember the hideous formula from the previous slide. There is no point in, you have to do this whole thing all over again, every single example. You have to put y equal to zx, and then you have to carry out the thing. So, what do we get? We integrate 3 log x plus log of 1 minus 3z squared equal to C1. Why the 3 log x? I have multiplied the differential equation by 3 conveniently. Otherwise, there will be a 1/3 floating around, but that is the thing. So, and then C1 is a constant of integration. Okay, exponentiate both sides to get rid of the logarithms, and you get x cube into 1 minus 3 z squared equal to C2, where C2 is e to the power C1, one constant is as good as any other constant, exponentiating a constant gives you another constant, correct. So, you get now you have to remember that you can't have z floating around, it has to be in terms of x and y. First term gives you x cube, second term will give you 3xy squared equal to C is the general solution of the ODE. They have solved the ODE. So, is it clear how homogeneous equations are to be solved? So, your first tutorial, there are problems for you to write, you can jot down these problems and work them out. This is the first tutorial, you can work them out during the first tutorial class. Maybe in the afternoon we could take some time off and try out some of these exercises. Please jot it down. Here is a slide of problems for you, please write them down. Please write down these exercises. Some of these are quite interesting. The first one says solve x cube sin y prime equal to 2 and find the particular solution such that yx tends to pi by 2 as x tends to infinity. See, when you solve the differential equation, there will be a certain constant c, right, constant of integration, there will be a general solution, and these kinds of conditions that are given to you, no, yx tends to pi by 2 as x tends to infinity, those conditions will enable you to nail down the constant, and what you get is called a particular solution. So, here the question asks you to determine the particular solution given some condition at infinity. When you solve the differential equation, that is a what kind of a differential equation is it? X cube sin y prime equal to 2. It is a variable separable equation. It is a variable separable equation. The second question is a geometrical problem. The second question is a geometrical problem. You have a curve with the property, the plane curve. It is a plane curve with the property that all the normals pass through a point. Take this point to be the origin and get a differential equation. Solve the differential equation and check that the curve is a circle. The only curve that you can think of with this property is a circle, right? All normals will pass through the center. For a circle, the normal must always pass through the center. You have to show that. Now, you have to show that if all conversely, if all normals pass through the point, then that curve is a circle. The circle is the only curve with that property. And then the other exercises are numerical. I mean, it's more like in the fourth problem, there are 3 pieces. Item 1, item 2, item 3. The differential equations are the same in all of them, but the initial conditions are different, right? Y of 0 is given to you in the first problem, y of 0 equal to 0 in the second problem, and y of 0 equal to 1 in the third problem. This is also a variable separable equation. So, how would you solve it? Y prime equal to y into y squared minus 1, or dy by dx equal to y into y squared minus 1. You would want to say dy divided by y into y squared minus 1 equal to dx and integrate it. That is the obvious way to go about it. That will work in the first piece. In the second piece, what is given to you? Y of 0 equal to 0. So, you cannot divide by y into y squared minus 1. So, how to tackle this problem? We are stuck. You can't divide because y of 0 is 0. Correct? We shall discuss in the afternoon, and maybe you want to probably come up with, you want to think about this at lunch, maybe perhaps you want to discuss with your colleagues at lunch as to how to cope with this situation. The same problem will come with the third one also, y of 0 equal to 1. You can't divide. So, this is a little bit of a interesting puzzle for you for discussing at lunch as to how to get around this problem. Question numbers 5 and 6 are again some hints are given to you. You just carry out the hint and it will. Shall we proceed then? Have you written it down? Okay, good. Now we are going to come to some very interesting phenomenon which you have probably not encountered before. Take a parabola. The next question is, take a parabola y equal to x squared. Find the equation of the tangent to the parabola at c comma c squared. Now you have a family of tangents to a parabola. What is it? It is a one parameter family of curves. And what are you asked? Find the differential equation for the family. Remember the very first problem that we solved. We took a one parameter family of circles and we found the differential equation. This time I am giving you a one parameter family of straight lines and asking for the ODE. And what are these straight lines? They are all tangents to a parabola. Okay. Now you come to the next topic. Clairaut's equation. Clairaut's ODE. Clairaut's ODE is ODE y equal to xy prime plus f of y prime. Now, is this a linear ODE or a non-linear ODE? Let us look at the various terms. Y, that is a linear term. Xy prime, is it a linear term or a non-linear term? It is a linear term because the non-linearity would be in y. We are looking at non-linearity in y. The third term, f of y prime, that is the problematic term. That is what is causing the differential equation to be non-linear. This is what is called as a fully non-linear differential equation because the derivative. See, for example, f could be the square function, f of t equal to t squared. So it could be f of y prime. F of y prime could be y prime squared. So the derivative is appearing in a non-linear fashion. So this is called a fully non-linear differential equation, and this particular differential equation is called Clairaut's differential equation. Now, which normally don't do this at all. When you have a differential equation, you want to integrate. You would not want to differentiate, right? You would not want to take a first order differential equation and differentiate and get a second order differential equation. Generally, that's not done, but there are certain special cases where differentiating the differential equation is essential. Now, okay, let us do it and let me tell you why that is advantageous in this case. Suppose you differentiate the ODE, what happens? You get the y prime, of course, cancels out from the left hand side and the right hand. That is an accident because the Clairaut's equation is very special. But look at the last term, f of y prime. When you differentiate that term, what happens? You get f prime of y prime into y double prime. So, although the differential equation was fully non-linear, when you take a fully non-linear differential equation and you differentiate it, the resulting differential equation is a higher order differential equation, all right, but it is not fully non-linear. The y double prime term is still appearing as a linear term. This is a very important observation. Whenever you take a fully non-linear differential equation, you differentiate it and you get a higher order differential equation, but it has the advantage that it is linear in the top derivative. So, this is very frequently done when you study partial differential equations, but here it is an ordinary differential equation. Okay, so the y prime term cancelled out, and then what happened? Then you have two factors, right? Y double prime into x plus f prime of y prime. Is that correct? Now you have to consider two cases obviously, y double prime equal to 0 or f prime of y prime plus x equal to 0. Y double prime equal to 0 is very easy to solve. What is the solution? Mx plus c. y equal to mx plus c. Two constants of integration, m and c. Why two constants of integration? Because we have differentiated it and we have obtained a second order ODE. But what are the original differential equation? A first order ODE. So there cannot be two constants. The second constant has appeared because we have performed an extra differentiation. So now what is the way out? The way out is take that y equal to mx plus c and put it back into the differential equation. What do you get? You get one of the constant in terms of the other constant. It turns out that c equal to f of m, correct? So what is the solution? Y equal to mx plus f of m. Is that correct? Right? Y equal to mx plus f of m. That is the general solution for the differential equation. General solution containing one arbitrary constant. But now there is something more, right? What is the other thing left out? The other case, f prime of y prime plus x should be equal, can be equal to 0. That has to be considered separately. Okay, let us do that. Thus, y equal to mx plus f of m is the general solution of the ODE. Assume that f is not a linear function. If f is linear, then f prime is constant, right? Then that is not very interesting. Then the second case will not be very interesting. Right? So let us assume that f is not a linear function. Let us assume that f double prime is not identically 0. If f double prime is not identically 0 means what? Let us take an interval where it is not 0. Let us take an interval where if it is not 0, it has to be either positive or negative, correct? And on an interval, let us assume that f double prime is continuous. Then if it is not 0, then it cannot change sign, intermediate value theorem. So let us assume that f double prime is positive on an interval, and let us focus on that interval, correct? So if f double prime is positive, that means what? That means that f prime is strictly increasing, correct? And if you have a strictly increasing function, continuous function, then it is invertible. You can find the inverse. You ever think of a strictly increasing function? Will it be 1 to 1? It has to be 1 to 1 because it is strictly increasing. I am looking at continuous functions. So image of an interval is an interval. So you have a 1 1 map from an interval onto some other interval. It's a bijective function. You can invert it. So f prime inverse exists. So let us look at the condition. What is the second condition there? F prime of y prime plus x equal to 0, and f prime is invertible. So I can invert it and get a one more differential equation out of it, which we can solve and get another wonderful solution. That solution is going to be called a singular solution. Why is it called a singular solution? Because it is not a part of the general solution. What is the general solution? It is written right on the first line, y equal to mx plus f of m. That is a general solution containing one arbitrary constant m. There is a family. If you graph it, it is going to be a family of straight lines, correct? And the singular solution, it is called a singular solution because it is not a part of the family. It is not a part of the general family. And you would be interested in knowing what this singular solution is. This is a peculiar phenomenon that you see, and the only reason why this is happening is because the differential equation is fully nonlinear. Whenever you look at differential equations that are fully nonlinear, appearance of singular solutions is a phenomenon. Before I talk further, it will be very interesting to look at all these things with respect to a specific example. We should study a specific example in C, right. So, let us apply all these things to a very specific example. Let us take the differential equation y equal to x y prime plus 1 over y prime, correct. Okay, so it is a Clairaut's equation. Differentiate the differential equation, the y prime term will cancel out, and you will get y double prime equal to 0, or the other thing, y prime squared equal to 1 over x. Y double prime equal to 0 will cause y equal to mx plus c. Substitute back into the differential equation. What are you going to get? Y equal to mx plus 1 over m. That is the general solution, giving you a family of straight lines. Now, let us turn to the other one, the interesting one, the odd man out. Y prime squared equal to 1 over x. What does that give you? That gives you y prime equal to 1 over root x. Take the two signs separately, analyze them separately. Take the plus sign. So, y prime equal to 1 over root x. You can integrate it immediately. What are you going to get? Y prime equal to 2 root x plus a constant. But now, by our experience, we should be careful, because we have performed a spurious differentiation, right, and we obtained it. And so, always substitute this back into the ODE and see. The constant may not be there actually. It might be a genuine constant of integration which is supposed to be there like the general solution, or it could be a spurious constant produced by our additional differentiation. Okay, so we should be very clear about this. So, take the solution, substitute this back into the ODE, and we realize that this C is 0. This is not the fake constant of integration that is produced by the extra differentiation that we have performed. Okay. So, we got two singular solutions, y equal to plus minus 2 root x. The general solution is y equal to mx plus 1 over m. And you can obviously see that y equal to plus minus 2 root x is not a part of the family. Why? Because it is a parabola. Y equal to plus minus 2 root x is a parabola, and a parabola is not a part of the general family of straight lines, right. Whereas, what we are having here is a one parameter family of straight lines. So, you see a very interesting new phenomenon we see when you have a fully nonlinear first order ODE, it can have singular solutions. So, you see that the theory is not just some come on let us solve it method of undetermined method of separation of variables, homogeneous equations, and those are important, and maybe you are familiar with all those things, but there are very interesting special things happening. Now, let me give you a very nice example of a singular family. Right. Yeah, no. So, we have this one parameter family of straight lines. Now, I do not know whether you have seen this. When I was a kid, the doodhwala used to come to our doorstep, and we used to take a metal bowl to collect the milk. And as a kid, I have noticed that whenever you see, so there is a light, then in the lobby there is a light, you will see a curve, a very bright curve on the surface of the milk. Have you seen that? When you are drinking tea from a metal cup or even a porcelain cup with which is being sort of glazed porcelain cup, you will, and when you see it in light, you will see certain curves which are very bright. Have you noticed it? What are those curves? Huh? They are called caustics. They are called caustic curves. What are they really? How do they arise? You have the rays of light, correct? Those caustics are envelopes of these light rays. What is an envelope? You have a one parameter family of curves. An envelope is a curve that touches every member of the family. So if you plot this parabola you will check touches every member of that, every member of this family of straight lines. The earlier exercise I gave you a parabola, right? Y equal to x squared. I said write down the equation of the tangent at c comma c squared. You get a one parameter family of tangents. Find the ODE. At that time it looked like a boring exercise. Now you will realize that ODE is a Clairaut's ODE. That is a Clairaut's ODE, and those straight lines, because you obtained the differential equation from the one parameter family of straight lines, that one parameter family of straight lines will be the general solution, and the parabola will be the singular solution. And that parabola and these straight lines were all touching the parabola, and the parabola is an envelope of the family of straight lines. That is an envelope. So once again, what is an envelope? Given a one parameter family of curves in the plane, let us stick to planes. An envelope is a curve that touches every member of the family. Is it clear? And now in geometrical optics, light is supposed to the light rays are straight lines, and those caustic curves are envelopes of this straight line, family of straight lines. That is what you see in the bowl of milk when contained in a metal or a porcelain, glazed porcelain dish. We will continue this in the afternoon. It is 11 o'clock, it is time for tea.